Hi, everyone. Thank you for joining us today for our Measuring G 3 Ways webinar. That I will pass it on to your presenters, Fran and Josh.
Hello. So I'm Fran, and I'm the Director of Physics here at Vernier, and we're going to be talking about doing acceleration of gravity 3 ways. I do want you guys to have some time to chat with each other about things that you do in the classroom with determining the acceleration of gravity or the gravitational field strength of the Earth. But I'll let Josh go ahead and introduce himself. He's helping me with this webinar today.
Hi, I'm Josh. Like Fran, I'm a physics specialist here at Vernier. We're both very familiar with the Vernier equipment as well as classroom practices. We both are teachers prior to coming to Vernier, and we're excited to learn together today.
All right. So first thing is, do you have graphical analysis already? If you do not have graphical analysis already, type it into the chat or into the Q&A that you do not have it, and I'll show you how to get that. Because what I'm going to do today is use Graphical Analysis Pro, and you need to have graphical analysis in order to get into Graphical Analysis Pro. And then if you don't have Graphical Analysis Pro, I'm going to give you a code that expires on October 4th. And that's also found in the resources in the shared folder that Angie just posted in the chat. So that shared folder includes an item called Notes for Measuring G 3 Ways, and that has the link to download graphical analysis, and I'm also going to show you right here. So let me go ahead and share my screen. So here is my graphical analysis, or here is our Vernier website. So this is just www.vernier.com. And in order to find graphical analysis, you go to downloads, or you can just use Josh's link. And then on the downloads page, more info here. And this is also where you can send your students to get it. And then depending on your device, you've got download for Windows, for Mac, the Chrome Web Store, the App Store, and Google Play. One thing that is a common error, I guess, on Chromebooks, you can see the Google Play Store as well as the Chrome Web Store. On Chromebooks, you want to make sure you get it from the Chrome Web Store, because if you get the one for Google Play, that's for Android phones and tablets, and it will not work on the Chromebook. You'll just get a blank white screen. You'll be like, okay, now what do? I can't do anything. So yeah, definitely you need to make sure you're getting it from the Chrome Web Store if you are on a Chromebook. And so Bill, I see you saying you don't have graphical analysis, we're using Logger Pro. Sure, yes, this webinar is still relevant because everything that I do on graphical analysis and Vernier Video Analysis can also be done in Logger Pro. I'm just using these more recent software versions because these are the ones that people are winding up having to switch to, but the experiments, all the instructions for the experiments are pretty much exactly the same on either platform, with just differences in which button you push and which menu you go to. So that's where you want to go to get your graphical analysis. And I'm going to switch us over to graphical analysis window. This graphical analysis is what you want to see when you open graphical analysis. And when you do that, this is where you're going to put in the free license key for graphical analysis. So this key, as I said, it works up until October 4th. There we are. So you type in that license code. I like to copy and paste it because it makes sure that you're not going to get it wrong. And let's see, yes, and Josh typed it in as well. So once you do that, you put submit, and then you are in. And I'm going to see if I can show you 2 things at once here. Let's see. I wish there was a way to easily do screen sharing plus show you things on the camera, but I'm gonna have to kind of go back and forth here. So right now, I'm going to connect to Photogate. And so I'm going to click sensor data collection here. And this is the only Photogate that I've got locally. So I'm going to go ahead and connect to that. And Picket Fence Freefall is actually the one experiment that you don't actually have to change any channels for, because you're just going to get a graph of object velocity versus time. So I'm going to go ahead and say done for this. And then I'm going to go back to seeing me. And I'm going to come over here to my setup where I have the Photogate up on this ring stand, and I've got my picket fence. And this experiment is experiment number 5 in physics with Vernier. And if you have the electronic version of physics with Vernier, it tells you how to do it in graphical analysis and on the LabQuest. But on the written version that you have in the book, it actually tells you the instructions specifically for Logger Pro. So whatever you've got, you can use, this is the Go Direct Photogate. You can also use the regular, I've got black on black here. That's terrible. I should have worn a different color shirt. You can cook it up with your LabQuest or your, whatever you've got. And then tips and tricks for this. A lot of kids like to just hold the, here, I'm too high now. They just hold the picket fence and then drop it. And the problem with just holding it is that they might fall at an angle, it falls and it hits the picket fence, or it hits the Photogate, and that is not helpful. So what I always teach students to do is to hold it by just your 2 fingers, your very, from the very center of the picket fence, and then just let it go very carefully. And we do recommend that you mount the Photogate using its accessory rod. If you don't mount the Photogate, you wind up with errors in the measurement. And that's not great. So I'm going to go back. I'm going to go ahead and collect a set of data here. So I've got that set up. Just drop it through. And I'm going to share my screen with you. So let me go back to screen sharing here. Which of these screens is the actual graphical analysis? All right. I don't need to know that it's going to expire in 12 days. And way over here, this tiny little bit here is where I got my data, and somehow it still wants me to collect data. So I'm going to hit stop. So now this is the data that I have. It's way over here in the corner. That's terrible. So clicking on this icon here, the magnifying glass with the little box in it, zoom to all data, and there is the entire data set. If you don't like it as a line, if you go down to edit graph options here at the bottom, you can turn that into points. You can have points or lines or both. Doesn't really matter. You can change the x-axis range. For this experiment, it works out pretty well just to leave it auto scaling so that all of the data fill the screen. But you can also change these options to always show 0, to scale it manually, whatever you want to do. But this is one where it works out well to just leave it, and you can then add a title as well. So here's a graph of velocity versus time. And of course, we want the slope to get us the actual acceleration. And so we get a nice linear fit. Linear is the default, but there's a whole lot of other options here. That if you scroll down, there's even more at the bottom outside the window. Or you can create a custom fit, but linear is fine. Slope, whoa. Okay, who was expecting 9.8? Raise your hand, or you say yes in the chat. Normally we don't get quite exactly 9.8, so I'm kind of surprised. Usually we get something like, oh, it's 9.76, or 9.93 or something, but okay, so got 9.8. So that's great and all. But what this experiment asked the student to do is actually to collect data 10 times and then to take all of that data and look at the averages. So I'm going to go ahead and collect and collect and collect and collect. And let me do one more time here. All right. So I just took a whole bunch of data. Where did that data go? So it all goes into all of these data sets. So you can see all of them at once by selecting all of them, toggling them all. And now I can see all of them. Again, it scales to show all of them. So they all look pretty steep here because they all started at slightly different times based on when I started the data collection. And then I can put the curve fit on all of them. And now I can actually go through here and one by one, I can read off the curve fits and write them down in a data table or whatever. So first I've got 9.84, then I've got 9.8, then I've got 9.817, 9.828, 9.818, 9.763. See, these are all the values that I was thinking I was going to get. So you can get all those at once and just the students can write them down and get an average. And then what I always did with this lab, I've got two variations that I like to have the students do. So I'm going to go ahead and stop sharing my screen again and actually come back to my other camera. So I'm just seeing my face here. So one thing that I like to do is change the mass on this. So I've got some clay here and I've already rolled it out into a strip. I have no idea how old this clay is. I think it's seen better days. But if you roll it out into a strip, then you can kind of put it around one of the black stripes on the picket fence. So it's not going to interfere. And now you've got a heavier thing, right? So you've got a heavier thing and you can now drop the heavier thing through the Photogate and see how that changes the results. Definitely make sure that it's only that it's not going beyond the edges of any one black stripe. All right, and you can do this. You can put them on as many black stripes as you want, just as long as you're not going into any of the clear spots on the picket fence. And then the other thing I do, and here I'll go back to this camera again, get rid of this thing. I've got this Rubbermaid box with some rubber bands. And I don't actually mean to have it as a guitar, but like we say in the book, in the experiment instructions, you can throw the picket fence up through the Photogate. I find that pretty challenging to do, but if you can get this set up with the right number of rubber bands, you can actually have that fling upwards pretty easily, and you get a different graph. So let me go ahead and collect some data with that. And before I do that, I'm just going to get rid of the straight lines. So I'm going to collect data. Let's see how well I do here. All right. Not sure about this one. Let me share my screen. I only got 2 points there, so that's not good. Let me try that again. So collect, and then I think I only got a couple points. I don't think I got any points there. Yeah, so this is a little bit tricky for students. Ooh, there we are. That's interesting. Let me try one more time here. Ah, not bad. Okay. So for this one, I think the important part is this part, and you can see that I've just clicked and dragged across to select it, and then I can do the curve fit there. And again, I get this 9.826, very nice. I try to have the students do that as many times as they can. If they fiddle with the rubber bands, then that might be a little bit easier. I'm looking at my setup now and realize, oh, it was a little bit off. That's why I wasn't actually getting data before. So you get it going the other direction and they notice, oh, first of all, the slope is going to be positive, but the velocities are negative. Isn't that interesting? So kind of a neat thing to throw in there. But if they do this another 10 times and get another average, then they can compare all their averages and decide, what's going on here? What does affect how fast something accelerates when we're close to the Earth here? Let me go back to stopping sharing. So Picket Fence freefall, pretty straightforward. Couple of things where you got to tell the students how to drop the picket fence, making sure that you are using your different accessories like your rubber bands and your shoe boxes, because everyone knows that physics is not a thing of just sensors, and you've got a lot of other toys. Speaking of other toys, the next thing I want to do with you is ball toss, which is another slightly tricky experiment in terms of the details. But once you get it right, then it gives you some nice data. So for this one, let me come back to the widescreen. I've got my ball. I'm going to get rid of this and bring out instead, let's see, I had it here. Oh, there it is. I'm going to be using the Go Direct Motion. You can also, of course, use the motion detector connected to, again, LabQuest Mini. They've got the same sensing element in them. So you're going to get pretty much the same data from either of them. And we're not going to be tossing this ball too high in the air. So either one of these will be fine. Then we usually like to use one of these wire in boxes just to protect the motion detector. I've seen other teachers pile a couple of textbooks on either side. Probably this Nerf volleyball is not actually going to damage the Go Direct Motion or even the other motion detector where the sensing element is a little bit closer to the plastic surface. The Nerf is pretty good, but you might not have a Nerf ball. You might have something else, and you just want to be careful. Once you damage that sensor, it's really difficult to actually repair that device. So I'm going to go ahead and turn that on. And for graphical analysis, let me go back to sharing my screen with that. So for graphical analysis, I'm going to do a new experiment. It's always a good idea to do a new experiment when you're switching sensors, just because the software will, if you try to switch sensors, it'll keep all the old data. It's a little bit confusing. It still thinks that I want to use the Photogate, but down here in the bottom right-hand corner is the sensor setup menu. And in the sensor setup menu, this is where you can say, all right, let's disconnect the Photogate and connect the motion detector. And you'll know that you're connected to the motion detector because the motion detector actually starts ticking. I don't know if you can hear it, but you can certainly hear your own. So I'm going to say done there. And here is my graph, but I'm going to go back to the camera here because here's where it gets tricky. because the motion detector, of course, it's going to reflect sound off of whatever's closest to it. And it starts detecting right at about 25 centimeters away. So you got to make sure you're about 25 centimeters away, or you're not going to catch it. It's just going to read a flat value. 20 centimeters probably. But then if you just throw it upward like that, notice how my hand stayed below the ball. That's great for catching the ball, but the motion detector is only going to detect my hand. So the trick is to kind of hold it with both hands on either side and fling it upward so that it goes up and down in a pretty straight line and stays over the motion detector the whole time. So typically you have to do this a bunch of times and then look at your data and pick out one result that's good. So I'm going to go ahead and start collecting data. And this is set to collect data for 5 seconds. So we'll see how many I can get. 5 seconds. All right, I got a few. So I'm going to show you what I got. All right, so here's my graph. I got a toss here. I got a toss here. I got a toss here. And I got a toss here. So kind of to me, I'd have to choose between these first 2 tosses for getting good results. I'm going to go ahead and select that one. And then I'm going to zoom in on just that feature. And so here, where we're looking at just that feature, that's just the part of the graph that gives a good result. And this is kind of like a good thing. I'm going to go back to this big screen here to teach students about which data are relevant and which data can be ignored. I know that with the motion detectors, a lot of times you get things like this bit here, which is clearly not something that's going to be useful. Or we've got these little pieces that are these little spikes. And sometimes you get spikes that might go completely up and down the screen, and it's confusing. So that to teach students, all right, let's just take the relevant data points and let's just look at those. And actually, before I do that, let me also bring up a second graph of velocity. So here's my velocity graph. And again, this is even harder to tell what's going on because of this dip here. I can try zooming in a little. It's still not great. So a couple things. First, you too can work with this particular data. So I'm going to share this out to you. If you are currently using Graphical Analysis and you went and you entered your code for Graphical Analysis Pro, then you can enter this ID, oh shoot, O0WM. Let me see if I can copy that and paste it. That did not work. Copy it, paste it. If you paste that code into your, why is it like that? All right. If you copy and paste that into your data sharing by going and clicking on that little icon to be able to see that data, you should be able to get this data on your own screen. And I'm sorry, I do not know why it is only why I have to scroll this thing. It's really awkward. All right, let's see if I can do that. Nope. It's not making my window wider would do it, but that did not do it. Okay. Anyway, because then you could also play with this data yourself. Any data that is shared to your students this way, they do not get your analysis unless you put the analysis up for them, and then they can get the analysis. But if you just give them the data, say this way, then you're saying, okay, here is some data, you get an analysis. And again, in Graphical Analysis Pro, we also have some built-in experiments. So sample experiments, C experiments. I'm going to filter this. So I'm looking just at physics with Vernier. And then this one is the ball toss. And this one is a much nicer looking data set because someone practiced a long time to get this particular data. So this is an alternate thing, is you can share this with your students. You can say, all right, students, you have access to Graphical Analysis Pro. I want you to go and open this experiment in Physics with Vernier. It's the ball toss experiment. We provide a video in this case. The video is not something you can do analysis on. It's simply showing what the experiment is. So in this case, it is a basketball and it is being thrown in the air. And here is our very nice data for that. Notice that our very nice data for that on these two graphs looks like it's off kilter from each other. This graph goes from 0 seconds to 5 seconds for position versus time. The velocity versus time graph goes from 0 seconds to 1.4 something seconds. In either case, again, students have to pick out the correct data to analyze. In this case, you might want them to graph the quadratic for this, for the position versus time graph, and then the slope of the velocity versus time graph. All right, I'm going to see what this is for this particular one. Here, my slope is negative 9.382. All right, that is not close to, well, it's sort of close to 9.8. It's not as close to 9.8 as I got with the Picket Fence free fall. And I'm going to stop sharing this so we can talk about that a little bit. All right, so who knows why I got a value closer to 9.8 with Picket Fence free fall than we do with ball toss? Feel free to type your suggestions or guesses in the chat, or maybe you already know. You can go ahead and type your answer in the chat. Or in the Q&A, either place. Air resistance, okay. Good suggestion. Some drag effect, okay, good suggestion. So how would I reduce the drag on either a basketball or this Nerf volleyball? Like if I were to, so if I were to use a different object, for example, what different object could I use? Okay, I suppose I could throw a bowling ball in the air. I'm not sure even my inbox would survive if I didn't manage to catch that. So before you all go trying to toss bowling balls over your motion detectors, I will tell you that even if I were to use a bowling ball, you're not going to get as good results with the motion detector. And that's because your motion detector is working on ultrasound. And ultrasound travels at the speed of sound. And when the ultrasound hits the moving object, then by the time that ultrasound bounces back to the detector, your object has moved in one direction or the other. And when you've got that motion in one direction or the other, you're not actually getting the correct value for the distance at that particular time. And those errors accumulate. So it's not just drag, though I believe there is drag in this situation. It is also the fact that you're using ultrasound instead of light. And so with the Picket Fence and the Photogate, you're breaking a light beam that goes across. And so it's going to be, you're going to get much better results with the Picket Fence. Bill, that sounds awesome. I'm glad you do that. As long as it's not a bowling ball, I would definitely still feel nervous if it's a bowling ball. I've used those weighted exercise balls. They're great. My trainer has had me sometimes raise them up over my head and slam it on the ground, which can be very therapeutic, as well as making me stronger. So final way that we're going to do G is using Vernier Video Analysis, and this is directly in a browser. So let me again pull up my browser. All right, so here I am, and for this, there is a link and a key again in the Google Doc. And I'm also putting, oh, Josh and I are both getting that together. So I'm just going to put that up here in the address bar, the URL bar of the browser. And it's going to recognize that key and give me, it's going to open the app. So one of the things that's really awesome about Vernier Video Analysis, it works on any device with a browser. So they just need that link or the key. And you'll also see in the Google Doc the way to get a free trial for this, but you can use this and you can share this key with your students for the next 12 days. Again, it expires on October 4th. So for this one, since we're doing falling objects, acceleration of gravity, I'm going to grab ball drop here and pull that in. And in this mode, we can simply just play the video and watch the ball drop. I think this video is hilarious because the ball does not bounce at all, which is very unexpected. It's just that it's trimmed so carefully that it starts with the first frame you need and it ends with the last frame you need, and you don't need any other frames. So I'm going to do a couple things before I get into the analysis here. First thing, I don't want to mark every frame. It's going to be a lot. I'm going to mark every 2 frames, and hopefully that'll be good. And you can change that value within these parameters. We only have those integer values for you to do that. And you get that through this little gear that's in this bottom row here. And then I'm going to go ahead and add my dots right over that basketball. Now I look at that and it's hard to see the basketball under where I put that dot. So I turned off trails. I'm going to turn them on again in a moment, but just for now, I'm going to have them turned off. Okay, I think it's moving enough now. I can turn them back on. I just needed it so that the basketball was out from underneath the previous dot in order to be able to make that dot, the next dot. And I'm actually not going to do the one on the ground because I suspect that's not really going to be where it would be if it were still falling. So you can see that my data show up on the graph and in the data set. And the data are the X and Y position data in pixels. Well, it would be nice if we didn't have it in pixels, but if we had it in something nice like meters. So I'm going to go hit the system button here. And there is a meter stick in the picture. Now you can zoom on here. And you zoom in, that can help you place the ends of these circles and the ends of the line in the circles. And then zoom back out. So that's 1 meter. If I had a different, like if I knew how tall the building was, I could use the building as a scale. If I knew how tall this tree over here was, I could use the tree as a scale, whatever. Probably the tree wouldn't be great because it's probably closer to me, to the camera than the building. So building is best. Anywhere on, anywhere that's the same distance from the camera as the object you're measuring. So once I've got that, I can also place an origin. In this case, it's nice to put the origin right where the ball lands. You don't have to do that. Like a lot of times when we deal with things, we deal with them falling downward, but then we go ahead and have them going in the positive direction just for the convenience of the equations. So you can do that if you want. Make X straight down. Then you've got that nice upward parabola. In fact, I think I'm going to do that just for the heck of it. And now I've got my X and Y positions here. This is a lot of information on the screen at once, and my graph is small. So I'm going to change this so I'm not viewing the video anymore, and I'm not viewing the data table anymore. I just want to see 2 graphs. I want, now that I've made X my direction, I'm going to use just the X position and X velocity. And once again, I can do these same graphs here. I can do a quadratic curve fit on my position data. I can do a linear curve fit on my velocity data and see what I get. So now I've got a slope of 9.486. I've got 4.764 for my half acceleration. I'm kind of in between. I'm gonna stop sharing for just a sec here. I'm kind of in between my picket fence free fall value and my ball toss value. So that gives me, yet another way of determining G. And again, I would ask you to think about what's going to be the best result. Is there a best result? How would you explain why the results are all different? How would you talk to students? Would you do all 3 experiments, or would you do just one of the experiments? So what are your thoughts? What would you do to help students understand whichever experiment or experiments you're going to do? Why didn't I get 9.8 for the video analysis? Yes, it can be hard to place points precisely. Yes, and it does lead to, I like that word, waffly data. One more thing is the issue of scale. That meter stick was not in very good focus. It had a couple of Post-it notes on the ends of it to help mark the distance, but that made the meter stick appear actually slightly longer than it actually was. And using only a 1 meter stick when it's a 3-story building that something's falling off of, it's essentially, it's not giving as good a scale as you could get. So a better scale would be longer, if possible. Like I might have stood like one of our 2-meter long aluminum tracks outside and use that as the scale. And then the other thing is that meter stick was taped to the wall, and the basketball by nature couldn't be against the wall as it was falling. If it was against the wall, it probably would have like bounced off the wall at some point, and you would have seen some erratic motion. So the basketball had to be just slightly closer to the camera than the scale. It's surprising how much difference that makes. So to get the best results, you do want to make sure that your camera is as far away from the motion as you can reasonably be and get a good view of it. The farther away you are, then the better your scale will be compared to the motion. And then the other thing is to use a telephoto lens, or like if you're using one of those fancy GoPro things, use the narrow view. Yes, as Angie points out in her message, we're just about over. Glad you could join us. It was fun for me. I love these experiments. Nice basic experiments are great for getting to the fundamentals. And I hope to see you again in a future webinar. And if you have any questions, feel free to call us 888-837-6437 or use email physics@vernier.com.